Hello everyone, welcome to the lecture on uncertainty modeling in AI, and today we are going to look at parameter learning with complete data. Of course, I didn't invent any of today's material. I took most of the content for the first part of the lecture, in particular parameter learning for Bayesian network, from the unpublished textbook written by Michael Jordan, chapter 9. Unfortunately, this chapter is not available online, but I happen to have a copy of this chapter and I'll upload it into NUS Luminous. Please access it from there. I took the next half of the materials from the textbook written by Kevin Murphy, in particular the part on parameter learning for conditional random field as well as Markov random field from chapters 10.4, 19.5 and 19.6.3. I also refer to some of the other textbooks written by Simon Prince, Stephanie Kohler and David Barber. I strongly encourage every one of you to take a look at these materials after today's lecture. Hopefully, by the end of today's lecture, you'll be able to compute the unknown parameters of discrete and continuous directed graphical models, which is otherwise known as the Bayesian networks, using the maximal likelihood estimation and the maximal a posterior methods. We'll also look at how to compute the unknown parameters of Markov random fields using the stochastic maximal likelihood and the iterative proportional fitting methods. Finally, we'll look at how to compute the unknown parameters of conditional random fields using stochastic gradient descent. And we'll also see that the difficulty of learning the unknown parameters increases with these three different graphical models. So in lecture 2 and 3, we have learned the definition of a Bayesian network Markov random field as well as conditional random field. And in particular, we learn how to encode conditional independences, and we also learn how to do factorization of a joint probability distribution using the parent-child relation as well as the clique potentials definition for undirected graphical model. In lecture 4 and 5, we learn how to do exact inference on the condition that we are given the joint probability distribution. It can be in a factorized form. For example, for a directed graphical model, we know that the factorized form would be given by the parent-child relation as denoted by this expression over here, where xi represents the random variable of I, the ith random variable, and x pi of I represents all the parents of the this random variable of I. So graphically, we saw that this is locally, it's given by a graphical model that can look something like this, where this guy here is xi, and this collectively, these three nodes here are collectively known as x pi I, which are the parents of xi, the random variable of xi. And here in this in lecture 4 and 5, when we look at the exact inference of a directed graphical model, we assume that this probability distribution over here, the conditional probability distribution of xi condition upon x pi I, is given to us. And that means that we assume that if in the case where this x, the random variables are discrete random variables, we assume that the probability table of this guy over here is given to us. But what we did not explicitly represent in those lectures is that there is actually an unknown parameter, or there is actually a parameter where this random variable conditions upon, and let's call this random variable data, or it's actually an unknown set of parameters that defines the underlying parameters, the distribution of these conditional probabilities, which means that this particular conditional probability distribution, to write it more explicitly, it should be equals to P of x1 condition upon x pi I and theta I, where theta I itself is actually the parameter that defines this joint probability distribution. And let's look at an example over here where suppose that I'm given this particular probability distribution over here, xi condition upon x pi of I. So here I can have xi and all the parents of this random variable xi And this means that I'm going to exhaustively write down all the combinations of the random variable of xi, as well as the set of parents of xi. And here we can write this in terms of a probability distribution table, where this can be given by data 1, data 2, all the way to data of m, where m is the number of states or number of combinations of where xi and its parents make. And here what's interesting is that all these sets of numbers can be collectively denoted as data I, which is the parameter, the underlying parameter of this particular conditional probability distribution, and which is represented by this locally by this particular Bayesian network over here, where we include a parameter of data that is pointing towards xi, and to write it more explicitly, we'll include data I in this conditional probability. But in those cases in lecture 4 and 5, we assume that these are given. That means that these probability tables are all given to us, which means that we know the joint probability distribution of the directed graphical model. And in those cases, we can silently omit this set of parameters which is otherwise unknown. And similarly, for undirected graphical model, we usually write locally that it's given a click potential, where this click potential is a function of all x, the random variable x. And we usually write this as in this way, where this is a click potential. And in this particular case, we also assume that in lecture 4 and 5, we also assume that this click potential is given to us as a probability distribution table, or as a potential function table. And in this case, we will have all the combinations of the random variable x that is in the click of C. And we'll write out all the combinations of this, where this table here will be filled up with all the numbers, which can be denoted by data 1, data 2, and all the way to data m, where m is the total number of states in the click of C. And here, this probability table was assumed to be given in lecture 4 and 5, where we can actually explicitly write this set of parameters as data, and turn this click potential over here into this particular form here, where we directly write xc condition upon the unknown parameter of this particular click over here. Or otherwise, we can also write it this way: xc semicolon of data c over here. So this means that it's actually dependent on the set of parameters. And in lecture 4 and 5, we assume that this probability distributions, or the unknown parameters, or the set of parameters here, are all given to us, where we focus on answering the question of doing exact inference. Here, what I meant by inference would be what we saw earlier on, to answering the question of computing the marginous probability from the joint probability distribution, or any form of conditional probabilities, where we call this is a XF query node condition upon all the evident nodes. And here we have to assume that all the joint probability distribution, which means that data that defines the joint probability distribution, are given to us. So now in this particular lecture, we'll turn our attention into another unanswered question, where we are given the underlying directed graphical model as well as the undirected graphical model. This means that we know how to factorize this into the various factorization, depending on whether is it a directed graphical model or a undirected graphical model. But in today's lecture, we are going to look at the case where all the random variables are fully observed, and we'll look at how to learn the unknown parameters. This means that I'm going to write this factorization explicitly into this form over here that includes the unknown parameters. And we are going to look at, in the case where all the random variables are observed, and we're going to see how to compute the unknown parameters of theta I. So similarly for an undirected graphical model, we'll write it this way, where this is conditioned upon the data of C, the click potential, the unknown parameters of the click potential, and we'll look at the case where all the random variables are observed, and we'll see how to compute these unknown parameters from the fully observed data. So the problem can be defined as, given a set of n identical and independently distributed, or in short, IID, complete observations of each random variable, denoted by this set over here, where they are all together m number of random variable, x1 all the way to xm, and for each one of these random variable, or for each set of this random variable, I'm going to observe it m times. This means that I have x1 1 all the way to x m of 1, where I observe this set of random variable once, completely once, and I'm going to observe every set of this random variable n number of times. This means that I can rewrite this into n of 1 of n all the way until the random variable of m of n, and where this is the nth observation that I have for this set of random variable, this set of m number of random variables. And we'll see two commonly used approach to learn these unknown parameters, which is the maximal likelihood estimate as well as the maximal a posterior method. And we'll see that both of these methods can be applied to the Bayesian network, the MRFs, as well as the CRF. But we'll see that what's the difference between the three different graphical model when we apply these two general approaches. And as the name suggests, we'll find the unknown of the parameters that maximizes this particular likelihood for the maximal likelihood estimate method. So recall that I mentioned in lecture 1 that the definition of likelihood as well as the definition of posterior is that when we talk about likelihood, this means that it's a conditional probability of x conditioned upon theta, where x here has to be a observed random variable or a set of observed random variable, and theta here has to be an unknown set of random variable, or otherwise known as the latent or hidden random variables. So in this arrangement over here in the conditional probability, then we can call this as our likelihood probability. And in the case where we want to maximize the likelihood, this means that we want to take the argmax of theta over this likelihood joint probability distribution that we have. And in the case where we assume that each set of observation are IID, we can say that they are all independent of each other. This means that each set of random variables, observed random variables, they are independent on each other, and we can turn it into a product over all the n sets of observations. And it's important to note that here the IID applies to each set of observation and not each random variable. So there is a difference here. Notice that if I evaluate this out, if I expand this term over here, it becomes x1 1 all the way to xm1. This is my first set of random variables that is observed, multiplied by x1 2 all the way to xm2, and all the way to the probability of x1n and xmn over here. So notice that the set of random variables still stays intact within each probability or each joint probability distribution over here. This is because we are not saying that this set of random variable, each random variable are not independent of each other. But what we are saying here is that each set of observations are independent of each other, and each set of observation, it has to come simultaneously at an instance of time where we draw these observations, or we collect these particular observations from our data or collection or our studies. And hence, in this case here, we can see that the product only applies to the set of random variables, which is I equals to 1 to n here. And for the case of maxima a posterior, as the name suggests, we want to find the unknown parameters that maximizes the a posterior probability. And as I have mentioned earlier, that in the case of a posterior distribution, we write the probability distribution or the conditional probability distribution of the unknown or the latent random variable conditioned upon a set of observed random variables here. And this guy here, it better be a latent random variable. And we want to maximize the probability, this particular a posterior probability distribution over the unknown parameters, which is theta over here. And here we can, as we have learned in lecture 1, we can further evaluate or expand this posterior distribution of theta conditioned upon all the observations of x1 to xm using the Bayes rule, where we will simply flip these two guys around. So we will have the likelihood function over here multiplied by a prior distribution over the unknown parameters and normalized by the joint probabilities of x1 to xm over here. So this is going to be the normalizer. And we can see that the normalizer over here is a constant which can actually be cancelled out because it's independent of theta, as well as we assume IID in the set of observations, n observations that we have over the set of m number of random variables. Hence we can put a product term over here because they are going to be independent of each other. But also notice that in this case, each set of observations of I over I, the set of random variables, m random variables of x1 to xm, they are going to be observed simultaneously at a single instance of time. Hence, there is no product over m, x, or the individual random variable. This is because the individual random variables, they are not independent of each other. And here we will reach this particular form over here, which we can see that the maxima a posterior, or the learning of the unknown parameters, it's also dependent on a prior set of information that we have over this parameter. So that's the difference between a maxima a posterior and a maxima likelihood estimation. We'll first look at the single random variable of a directed graphical model. It's a special case of what we are going to look at in a general directed graphical model. But in this case, we only see that there is one single random variable. So here, this joint probability distribution, or there is only a probability distribution over this single random variable, which is written by the probability of x conditioned upon theta, where theta over here is our unknown parameters of this distribution. So what this means here is that if this guy over here is a discrete random variable, x is a discrete random variable, then I would have to write down all the states of x, and the joint probability of x conditioned upon theta would be given by theta 1, theta 2, and all the way to theta k, where these sets of entries over here in this table here are collectively known as theta. And the objective here is that we're going to learn the unknown parameters theta from n sets of observations of the this random variable of x. And what this means graphically is that for n number of IID observations of x, denoted by x1 all the way to xn, the directed graphical model, it becomes augmentation of n disconnected replicates of x. We can rewrite this into this form here, since each set of observations x1 all the way to xn, they are independent of each other because of the IID assumption. But each one of these random variable or each one of these observation is still dependent on theta. So for example, x1 here, it's going to be dependent on theta, and x2 here, the observations here, it's also going to be dependent on theta because the underlying parameter distribution is the one that leads to the sample of x being observed in every one of these observations here. And so we can see that this we will repeat this graphical model n number of times from x1 all the way to xn here, but they are all still dependent on theta. They are all drawn from the same probability distribution, which is denoted by probability of x conditioned upon theta here. And we can simplify this drawing over here by saying that all of the observations here are a direct result of the unknown parameters theta. And the objective here would be to learn the unknown parameters using the MLE method. We will see that using the MLE method, this is equivalent to taking the argmax of theta of the probability of x conditioned upon theta. And here, since we assume IID, this means that this guy over here can be rewritten into argmax of theta and the product of p of xi conditioned upon theta, because each one of these xi is IID to each other. And in the case of MAP, we'll see that we will be looking at the argmax of theta over the posterior distribution of this guy, and this can be rewritten into using the Bayes rule, as well as ignoring the normalizer because it's independent of theta. We can see that this term over here can be re-evaluated into the likelihood multiplied by a prior distribution, and taking IID among all the random variable, the observations of the random variable, we can rewrite this term over here to be xi conditioned upon theta multiplied by p of theta. So now let's look at an example on continuous directed graphical model under the distribution of a univariate normal distribution. So the problem here would be to fit an univariate normal distribution model to a set of scalar data. This means that what we are assuming here is that given the graphical model that we have looked at just now, where we have observed n number of IID observations of x1, x2, all the way to xn here, and these are all dependent on the unknown parameter of theta. We are assuming that the probability or the likelihood distribution is given by a normal distribution of x conditioned upon mu and sigma square here. And now the question over here would be to find the unknown parameter which is equivalent to mu and sigma square that defines this joint probability distribution table, because in this case the continuous directed graphical model. And so recall that the univariate normal distribution is given by this equation here, where we have two unknown parameters, mu and sigma. So our goal now would be to find these two unknown parameters, mu and sigma square, given that we have observed this random variable n number of times. Let's look at the first approach of maximal likelihood estimation to solve this problem. As we have seen in the earlier slide, that under the maximum likelihood estimation, what we are after would be to take the argmax over theta, the unknown parameters, on the likelihood function, which is given by x conditioned upon theta here. And since x, all the observations are IID to each other, so all these n number of observations of this one single random variables, they are IID to each other, they are drawn independent and identically to each other. It means that we can rewrite this expression over here into a product of the probability distribution over each one of the observation. And we also saw in the previous slide that the likelihood given by this probability density function, univariate normal distribution, which is given in this particular form. And this means that we can rewrite this guy here into this form, condition upon mu and sigma square, where we can plug this equation, the normal univariate normal distribution, into this equation. And now the maximization of the unknown parameters becomes a maximization of the two respective unknown parameters of the normal distribution mu and sigma square. So alternatively, we can also maximize the logarithm of this distribution, of this product of the independent and distributions over here, where we can see that we can turn the product term into a summation term, which can we will see in the later slide that by turning product term into a summation term, it will make the partial differentiation which we use to obtain the maximal likelihood estimation of mu and sigma square easier. And here we'll plug the equation of the normal distribution into this term here, and taking a log term of this normal distribution, we will arrive at this equation. We can see that applying the logarithm, it's actually a monotonic transformation, hence the position of the peaks always stays in the same place. But we will also see later, as I mentioned in the earlier slide, that this logarithmic operation, which turns the product into a sum operation, will make partial differentiation, which is the essential step in obtaining the argmax of the unknown parameters easier to evaluate. Here we saw earlier that to get the optimal mu and sigma square, which is the unknown parameters of the univariate normal distribution, we arrived at this particular form here, where we turned the product term into a summation term from the logarithmic operation, as well as plugging in the normal distribution into this equation here. And now maximization can be easily done. If we call this particular term here L, the total term over here, this as L, this means that we are, let's shorthand this with the argmax of mu and sigma square over L, where L is actually a function, of mu and sigma square in this term here. And we can see that the maximization can be done in closed form by simply taking the derivative of the variable that we are interested in optimizing over and equate it to 0. So we'll do it here. We'll start with mu first, where we take a partial differentiation of L with respect to mu, and by working out this partial differentiation, the calculus here, we see that we will arrive at this particular term here, where since we are taking the partial differentiation with respect to mu, we can see that the first few terms over here, they are all independent of mu and can be dropped off. And here, since this guy here is also independent of mu, it becomes a constant because we are going to equate it to 0. And by bringing the numerator terms here over to the other side, we can make mu the subject, and this is the final expression that we will obtain. And we can see that this optimal solution for the mean of the distribution of the univariate normal distribution, after we have observed the n number of observations which are IID to each other, we can see that this mean is essentially just the average of all the observations. And we can then proceed on to find the unknown sigma square, or the variance of the univariate normal distribution, where we'll do the same thing by taking the partial differentiation of L with respect to sigma square. And notice that here, sigma square is treated as one whole term by itself. We do not differentiate between the square term here, since we are looking at the variance as a whole. We are not looking at the standard deviation. And this term here, after taking the partial differentiation with respect to sigma square, we'll get this term over here, which we equate to be 0. And we do the same thing where we'll simply make sigma square the subject by arranging this equation into this form here. We'll be able to get the optimal solution of sigma square. Well, we can see that the optimal sigma square is given by the population variance, which we are all familiar with from the statistics course that we have taken earlier. So we can see that interestingly, finding the argmax over mu in a univariate normal distribution is equivalent to doing a least square operation. And here in the first equation here, where we take a argmax over mu over this normal distribution, which we have seen in the earlier slide, we can see that argmax over mu, the first two terms over here, they are independent of mu, and hence it can be dropped off from this argmax operation, and we are left with the last term where we can see that sigma square is independent of I, so we can pull it out into this constant 0.5 divided by sigma square here, where by taking an argmax over mu, it's a constant over mu, or independent of mu. Hence we can take the 0.5 over sigma square and factorize it out of the argmax operation, which we can ignore it, and we are left with argmax of mu over the negative summation of the differences, the square of differences between the x, which is our observations, and the mean value here, which we can convert this argmax over a negative into a argmean, and this operation here would be the least square operations. And here, let's take an example here where we know that if I were to do a regression where I need to fit n number of observations of points in a 2D space, x and y here, where I need to fit a straight line over here, and this straight line can be given by my equation of a straight line y equals to mx plus c, which is equivalent to a function of x, f of x. And here, if I were to give all these points over here, which I denote as x1, y1, all the way to xn, yn here, what I want to do here would be to take mu over here as my f of x, where this guy over here is my predicted values of y, and I want to take the sum over the negative, the difference of this predicted value for every x that I have. I want to take the difference between this predicted value of y and the observed values of y, so yi, xi over here, and I want to take over the square difference of this over the sum of all the observations that I have, and we can see that these two are equivalent. And what I want to do, but in this case here, what I want to do would be to argmean over the unknown parameters of m and c, and here we can see that we are taking mu, or the mean value, as our prediction of that is given by fx in the least square linear regression example here. So now let's look at the second approach in finding the unknown parameters, which is using the maximal a posterior method. And we have saw earlier that this can be done by taking the argmax over the unknown parameters over the likelihood multiplied by the prior term over the unknown parameters. And since each one of these observations here, we assume it to be IID, we can rewrite this term, the probability distribution, as a product of all the distribution over each one of the observation. And here the likelihood term would be again still the univariate normal distribution, which is given by this equation here. And we saw that in the earlier example that this normal distribution has two unknown parameters, hence we write data as mu and sigma square. And now the additional prior distribution, we will use the conjugate prior as what we have seen the definition of conjugate prior in lecture 1, and we'll use the normal inverse gamma distribution as the conjugate prior to the univariate normal distribution. So this is also what we have seen in lecture 1, where the normal inverse gamma distribution has 4 hyperparameters: alpha, beta, gamma, and delta, which we will use it to control our prior knowledge over the parameters, the unknown parameters of mu and sigma square, and it is given by this equation here. Now, plugging in both terms, the likelihood distribution as well as the prior distribution over the unknown parameters of mu and sigma square, we can see that we will get this equation here, where we will do an argmax of mu and sigma square over the logarithm of this product term over here, and we'll turn this product term into a summation sign, where we can see that it's easier, this particular operation, the sum operation, is easier to deal with when we do a partial differentiation to find the maxima of sigma and mu square. Now here, as I have mentioned, that we can easily find the optimal value for mu and sigma square by taking the derivatives of this whole term here, which we collectively call L, and setting it to 0. So we will first take the partial differentiation of L over the partial mu and equate it to 0. And by making mu as the subject, after we have gotten this particular equation here, we can see that we will arrive at this particular expression for the optimal value of the mean or mu over here. And we can see that this is the same, almost the same as the mu from the maximal likelihood estimation, where this term here is actually exactly the same as what we have seen in the maximal likelihood operation. But in this case here, we can see that the mu, or the mean that we obtain from the maximal A posterior, is skewed by the hyperparameters of our posterior distribution over the unknown parameters of mu and sigma square. And interestingly, what this means is that since this conjugate prior distribution, or this prior distribution, which consists of the hyperparameters of gamma and delta over here, what this means is that our prior distribution, or our knowledge of the prior distribution over the unknown parameters of mu and sigma, is going to guide us into skewing the result of mu, because these are prefixed or predefined based on our prior knowledge of the distribution. And in the case where we do not have any knowledge, we will simply assume a uniform distribution, where we will set this to 0, and this means that the mu would be equivalent, or the optimal mean that we have obtained will be equivalent to the optimal mean that we can obtain from the maximal likelihood estimation without any prior knowledge over the unknown parameters. And similarly, we can do a delta L over delta sigma square, equate this to be 0 to find the optimal sigma square value. And we can see that after this operation over here, we will end up with a sigma square to be equals to this expression here. And interestingly, we can also see that the same expression for maximal likelihood appears in this sigma square here, where now it consists of the additional terms from the hyperparameters, which is from alpha, gamma, beta, and of course mu over here. But in this case here, we can see that the hyperparameters from our prior distribution, this is from our prior distribution, it helps us to skew the results of sigma squares, which means that we are skewing the result from our prior knowledge. And in the case where we do not have any knowledge or any prior knowledge of the unknown parameters, we can simply set this to be 0, or the hyperparameters to be 0, and we can see that as a result, this solution here, the optimal solution from sigma square here, it degenerates to be the solution of the maximal likelihood estimate. Here's the plot to compare the differences between the maximal likelihood estimate and the maximal A posterior estimate. We can see that as we have more data points, this means that as we have more data observations, then the estimates between the maximal likelihood and maximal a posterior would become very similar to each other. This is because when we have enough data, we do not need to rely on the prior estimates from our conjugate prior distribution. So here, this guy over here, this guy over here is actually based on the prior knowledge that we have, or the prior knowledge that we set from the hyperparameters of our conjugate prior distribution. So if you refer back to lecture 1, we'll see that for a certain set of values of these hyperparameters of the prior distribution, which is alpha, beta, gamma, and delta, we'll get a certain distribution over mu and sigma square, and we can see that that distribution will look something like this, where it's going to be peaking at it's going to peak at a certain point. The probability distribution is going to peak at a certain value of mu and sigma square, and this particular plot over here that corresponds to the maxima prior. It's equivalent to the peak of the mu value here, which is this mu value from a certain setting of the hyperparameters, as well as the spread or the standard deviation that is obtained from this peak of the prior distribution that I can read off from here, the sigma square max, as well as the mu max, which I can plot, use these two values to plot to get this distribution of NP over here. And what's interesting here is that as we have lesser and lesser data points from 50 to 5 or even to 1 data point, we can see that in this case the deviation of the maxima a posterior with the MLE estimate will become larger. And what's interesting here, since we have less data point, we are going to trust our prior more in the case of the in the case of the MAP estimation. And we can see that this cross over here, the peak of our MAP estimation, becomes closer to our maxima prior distribution, which is the prior over our joint probability distribution. And in the case where I only have one data point, this is obviously not enough to estimate, do a MLE estimate, because MLE is purely based on data. This means that I'm only taking this distribution here, and in this case here, since I'm only dependent on all the data points, there's no prior term over here. And one data point, what it means is that one data point or one observation here is not insufficient for me to estimate the joint distribution. Hence, there's no cross over here, or there's no plus sign over here that represents the MLE estimate, the peak of the MLE estimate, and we are solely relied on, or the result is going to be much closer to the maxima prior term that we have defined using our hyperparameter. Since we have less data, what this means is that we are going to trust the data set, the observation less, and move closer towards the prior distribution that we have defined from the conjugate prior, or from our hyperparameters that defines the conjugate prior. And in the case where we have more data, we are going to move away from this maxima prior and trust the data more. Now, after having looked at the special case for univariate normal distribution, let's move on to look at the discrete graphical or directed graphical model, where we will look at the case of a univariate categorical distribution. And the problem here is to fit a categorical distribution model of k categories to a set of data of x1 to xn, where we observe this random variable x n number of times, where x here it's going to take one to k states, and we will denote each one of these observations with a basis vector that denotes, or one hot vector that denotes the state of the random variable. So for example, if I say that I have 0, 0, 0, 1, 0, 0, then this will denote that I have a k number of states, and in this particular case here, this means that the random variable is going to take the fourth state that I have out of this k number of states here. And recall that the categorical distribution is given by this form over here. So now we'll explicitly write this probability over one single random variable conditioned upon the unknown parameters here. So these are my unknown parameters, and in this case here, we have seen in the first lecture that under a categorical distribution, I would have a k number of unknown parameters subjected to the condition that each one of these parameter, it has to be in a range of 0 to 1, because each one of these represents the probability of x taking the kth state, and all the unknown parameters would have to be summed to 1. This is because each one of these is a probability of x taking a single state, and all the probability distribution of every possible state that the random variable can take better sum out to be 1 to make this a valid probability distribution. And here, let's start off from what we have seen earlier, the definition of the maximal likelihood estimate. We will take the argmax over theta, and since this likelihood function over here, it's IID, assuming that all the observations are IID, we can expand this or rewrite this into the product term of over every single observation of xi. And since the likelihood function is given by this probability density function that we have defined in lecture 1, we can directly plug this term here back into the argmax and to get this particular expression here. So we are interested, which means that we are interested in taking the argmax over the k number of unknown parameters lambda 1 to lambda k on the this probability distribution, which we take it as IID, hence there's a product term over here. But not forgetting to constrain the unknown parameters of lambda to the sum of all the unknown parameters has to be equals to 1, and hence there is a additional constraint over this optimization here. And now let us replace this general probability distribution with our categorical or univariate categorical distribution, which is given by this form here. And we saw in lecture 1 that this expression or this categorical probability distribution over x can be rewritten into this form over here, where it's a product over k categories, and lambda k would be my unknown parameters raised to the power of xik, where xik here, I is the index of the ith observation and k is the index of the kth state. So what this means is that if the ith observation takes k state, then this guy here is going to be 1 or 0 otherwise. And now since we are observing this guy over here over n number of times, so what this means is that I can rewrite this term over here. I can push this summation into this expression over here and rewrite this term where I take the product of 1 to n and lambda k xi k to be equals to lambda k xi k multiplied by 1k multiplied by lambda k x2k all the way until lambda k xn of k. So what this means here is that I can rewrite this exponential term over here. Since it's the product of the exponential term, I can rewrite this into lambda k xik plus x or x1k plus x2k plus all the way until xnk here. And since each one of these xik it's going to be either 0 or 1, this means that this term over here is equivalent to counting the number of times that xk, or counting the number of times of this observation that xk is equals to 1. Hence, I can rewrite this whole term over here as lambda k to the power of n of k. And hence, I get this final expression subjected to the sum of all the parameters k, or of all the k parameters must be equals to 1, which we can then optimize by applying the Lagrangian multiplier to get the auxiliary function, since this is a constraint optimization under equality, because this guy here is an equality constraint. It's an equality constraint. Hence, we can use the Lagrange multiplier method to do this. And by applying the Lagrange multiplier method, we can rewrite the cost function into this form over here. So this would be the regular cost function that we have in the previous slide. And by taking a log over this term, but this will turn the product term into a summation term, which can ease the operation of the calculus, the partial differentiation that we need to get the optimal value for the unknown parameters. And this guy over here would be simply the equality constraint, where we move the 1 from the right hand side of the equality to the left hand side of the equality, and we introduce an auxiliary variable which is called the Lagrange multiplier variable. And we can see that by taking the derivatives with respect to lambda k, each one of the lambda k, 1 to k, all the way to k, and the auxiliary Lagrangian multiplier v, and setting each one of these equation to 0, we can solve for lambda k, each one of the lambda k, and it would take the expression over here, where we can simply see that this is the average number of times that we have observed k, because we have seen earlier that nk here simply means that the number of times where we observe the random variable taking a value of k. So, and here it's normalized by the total number of observations that we have. Now let's look at the approach 2, where we apply a maximum a posterior on the univariate categorical distribution. So we'll start off by the same definition for maximum a posterior, where we take the argmax over the unknown parameters on the likelihood multiplied by the prior term. So the difference here, as we have seen earlier, that between the MAP and the MLE is the additional term of the prior. Here, we can see that the likelihood of a categorical distribution is what we have defined in lecture 1, and we saw earlier in the previous slides. And now we have also seen in lecture 1 that the conjugate prior of the categorical distribution is defined to be the Dirichlet distribution, which is given by this equation over here. So what this means is that by defining k hyperparameters, we will be able to define a certain prior distribution, or our prior knowledge over the k parameters of the univariate categorical distribution, as shown in this equation here. And notice that this would also be subjected to the parameters, the k parameters of lambda 1 to lambda k to be in the range of 0 and 1, as well as it must be summed to 1. So this is actually a simplex function. And we plug both the likelihood and the prior, or the conjugate prior distribution, into the argmax operation over the k number of parameters, lambda 1 to lambda k. And we can see that these terms over here from the prior distribution is independent of lambda, hence it can be taken out and ignored. And now merging these two terms, since it's a product, we can write the exponential term into a sum term, into a summation term. So here, where nk over here is defined as usual, as what we have seen earlier, we'll simply count the number of occurrences over the n observations of the random variables, and in this case we'll finally arrive in this equation over here, subjected to the sum of all the parameters better be equals to 1 to make it a valid probability distribution. We'll do the same thing since it's an equality constraint optimization. We'll use the Lagrangian multiplier to solve for this by introducing v over here, and hence we can combine the constraint, the equality constraint, with the cost function that we have seen earlier. And we'll also do the logarithmic trick to turn the product into a summation term so that we can do the derivative operation easily. And in this case, if we set this the cost function over here and partially differentiate it with respect to all the lambdas as well as v, and setting it to be 0 and solve for lambda, we'll get this expression over here. And what's interesting here is that we can also see that the regular term for lambda, it appears here from MLE, and with the additional terms from the prior, these alphas are actually from the prior distribution over our parameter of which is given by this guy over here, and it's from the Dirichlet distribution, or the Dirichlet prior, conjugate prior of the univariate categorical distribution that we have seen earlier. Here the intuition is that the prior knowledge that we have over the parameters of the univariate category distribution can be used to skew the results, or can be used to skew the optimal value of this lambda, the parameter of the univariate categorical distribution. And similarly, in this case over here, we can see that if we do not have any prior knowledge on the distribution over the parameters, we can simply set alpha here to be equals to 1, where this term over here simply drops off. Now we are left with the usual optimal value from the MLE estimate, because we simply do not have any prior knowledge over the unknown parameters.